This question's about bungee cords. It's a bit convoluted, so I'm going to start at the end. The last sentence says, you had several bungee cords to select from, and you tested them by stretching them out, tying one end to a tree. So here's our tree. You tied one end to a tree and pulled on the other with a force of 380 newtons. So there you've tied the bungee cord. You're pulling with F equals, for me it was 380 newtons, not important. And when you did this, what distance will the bungee cord stretch? So there's the 0 point. How much does it stretch out because of this force? So this is the question. How much does it stretch? Well, for all bungee cords, everything is F equals ma. That's the... Yeah, but there's no acceleration here. That's only if there's a net force. What am I saying? Force on a bungee cord or force on a spring is negative kx. So if you pull in this direction, the force on the bungee cord is going to pull in the other direction. The sign won't matter here because you're just, what is the distance? You're pulling 380 newtons to the left, so in this case it's going to be negative 380 newtons. You want to know what the distance is. We don't know. In order to answer that, we're going to have to find k. So working backwards, there's a question of distance. That's the question asked by the computer. In order to answer that, we really have to find out k. So a question of distance is actually a question of k. So can we use, the real test for us can we use the first preamble to figure out what k is? That's what we're looking for. And let's now start from the top, knowing that we're really after trying to find the stretchiness of the bungee cord. A bungee cord is 30 meters long. So someone's going to jump from a cliff, say, and they're going to jump. The bungee cord is going to stretch out, in my case, 30 meters before anything even happens. You might have some different length. And it's going to stretch. It's going to stretch some distance depending on, so if I call this, say, 0, and I call this this distance, now let's call this, let's call this, just to keep it in the same notation, I'm just going to call this delta x. That's how much it stretches. And we know forces on a spring, negative k delta x, negative kx. It'll be just x if we call this 0. It's going to be the opposite. So if this is some kind of negative distance, basically this negative sign means it's always in the direction opposite of your pulling. So it's going to be an upwards. I'm going to erase this and just say it's going to be upwards. The force is going to be upwards. Now this platform, it says, is at some height to the ground. In my case, it was 45 meters. And you've promised your uncle that he will fall a maximum of 41 meters. So you've told him that he's going to fall, okay, in my case, I told my uncle that his Y max, I'm just going to named it Y max, I'm not sure why I did, 41 meters. So you're standing there, you say that he's going to fall 41 meters, the height is 45, well, therefore you're really saying that he has about, he has some safety here of, well, that's not much, it's only 4 meters. So he has this distance here is 4 meters. You might want to give that a name. I'm going to call it S for safety. 4 meters. So you have a bungee cord. You figure out how much it's going to stretch because you've tested it. You think that from a height of 45-meter jump, he's going to fall 41 meters. Therefore, you know there's about a 4-meter space left there. Now, how can we use this? Oh yeah, the father-in-law has a mass of, in my case, actually it doesn't matter, but in my case, the mass is equal to, so there he is. In my case, his mass is 94 kilograms. So this is an energy homework, so you might want to think, wow, maybe we can use energy to figure out what K is. And yes, that's the case. Let's think about conservation of energy. Conservation of energy says the energy is not going to change. So that means the energy up here is going to equal the energy down there. Up here, now at the bottom, just as he stops stretching, he's not going to have any speed down here. He's going to have lots of speed in the middle, but that's an intermediate state. You just can look at the changes in energy from the top to the bottom. Up top, his kinetic energy is equal to 0 up here. He's not really moving just before he jumps. And at the bottom, at the very bottom, just as the bungee cord stops him, he's not going to have any kinetic energy there either. So there's really no, he's going to have plenty in the middle, but we're not actually worried about the middle. We're just going to jump from top to bottom. What kind of energy does he have up here? Well, there's no energy in the spring either because it's not stretched. There's a large amount of energy in the spring down here. That's going to be equal to energy of springs, or 1/2 kx squared. That's the formula. And x for us is this delta x, the way I've drawn it. And that was the difference between what did I supposedly promised in the question that he would stretch a maximum of 41 meters, given that the length of the rope was 30 meters. For me, the stretch is 11 meters. So we know how much energy is in the stretchy rope there, and where did that energy came from? Well, he lost. That's energy gained by the bungee cord. It had no energy up here in the flaccid bungee cord, and down here in the stretched bungee cord, there's all of this energy. 1/2 k. We don't know what k is. It's still an unknown to us. And where did that energy came from? It came from his gravitational potential energy. He lost a whole bunch of gravitational potential energy. So we had a whole bunch of potential energy of gravity up here. mg, however high this is, mgh, his h was 45 meters. And he has a much smaller amount of energy of gravity here. It's just mg, whatever height this was, that was 4 meters. So a whole bunch of energy is lost by gravity. You can calculate that exactly. And that's equal to the whole bunch of energy gained by the stretching of the rope. You can then solve for k, find k, put it back in there, find x. Good luck.